Hello everyone, Dr. Zia Tahir here. This video tutorial is 3D heat transfer analysis through rectangular fin using steady state thermal analysis and transient thermal analysis. So in this video tutorial, I'm going to solve this problem using steady state heat transfer and transient heat transfer. So it is a rectangular fin. So a hot surface is cooled by attaching rectangular fins to it, as shown in that figure. So the fins are mounted on a rectangular base plate having thickness of 1 centimeter. So that thickness of the plate is 1 centimeter, or you can see that height of the plate. The width is 8 centimeter. That width is 8 centimeter, and length is 6 centimeter. So thickness TF, that is the thickness of each fin, that is zero point 0.8 centimeter, and distance between two fins is 1 centimeter. So the fins are made up of copper with the density 9,000, thermal conductivity 400, and specific heat capacity 385. So the temperature of the base plate is 80 degrees Celsius, so that lower surface temperature is 80, and the temperature of the surrounding air 20 degrees Celsius, and the fins are cooled by air having convective heat transfer coefficient of 38 watt per meter square per Kelvin. So that all details about the problem, and determine the temperature along the length of the fin. So the temperature along, in this case, that is the height of the fin, along the height of that fin, using steady state heat transfer analysis and transient heat transfer analysis. So this video is a series, one of the video of the series of ANSYS work by thermal analysis, and uh, the previous videos on the same topic you can watch in that ANSYS Workbench thermal analysis playlist. So the steps to perform steady state analysis and transient heat transfer analysis. So these are the steps. So first I'll start project with steady state thermal, adding material. Then is a 3D analysis. So geometry in the design modeler need to create that geometry. Then assigning material, construction geometry path along the height of that fin, then performing mesh, and then applying boundary condition, that is a temperature on the base, and then convection on the rest of the surfaces. And then in the solution required is that temperature along that path, and then in the results to check that temperature. So then the temperature, that is a steady state. So the results of steady state temperature, they are going to define that how much is the temperature required for the solution to converge. So then comes the transient analysis, and in that transient analysis again boundary condition need to be applied, but the analysis setting number of steps required, so I am going to do it for 2 minutes or 120 seconds. And then in the material need to add density and specific heat capacity, because for steady state thermal only thermal conductivity required, but for transient density and specific heat capacity also required, and then the same solution is required, and then comparison of results from steady state and from uh, transient. So both results will be compared. So the first step is to start a steady state project, and for that one here you have ANSYS Workbench, and in the analysis system here is steady state thermal. So double click on that one, and then a steady state thermal, that is a project schematic. The project is steady state thermal, and these are the steps for steady state thermal. So need to save that project somewhere in the computer. So I've saved that as 3D rectangular fins in the computer. So next step in engineering data, need to add material, and only thermal conductivity for that steady state is required. So here in engineering data, need to add material, and here click here to add material. So I'm going to use that material copper, and the only properties available are thermal conductivity, either isotropic or orthotropic. So I'm going for isotropic, and thermal conductivity for copper is 400, and now that material is being created. So once you have created that material, you can save it. So once that material is saved, so you can just close that window. Next step is in geometry. I need to select analysis type is 3D. So here in the geometry and in the properties, analysis option is already 3D, and then need to start design modeler. So here are the steps. The next one, design modeler. You need to start design modeler. So right click on geometry and new design modeler. So here is a new design modeler. And in this design modeler, need to sketch that one. So that fin. So for this one, the front face of that, it can be modeled and then it is extruded. So for this one, I need to go here, select XY plane for that, and I'm going to sketch it in XY plane and change units to centimeter, because here most of the dimensions are in centimeters, so need to change into centimeters. And then here in the sketching, first go to setting in the grid, snap that, and then major grid spacing as 1 centimeter, and then minor is 5. Okay, so here you can see, so that is now that one. So I have zoomed it. So the scale is exactly 8 centimeters. So the base of that is 8 centimeter, and then that total height is 6 centimeter. So in the design modeler, now I'll go to draw and then polyline. And in the polyline, I'm going to start from there till that is 8, and then here it is 6 centimeter. Okay, so that is 8 and 6 centimeter, and then fin is zero point 0.8, so that is zero point 0.8, and then that is 1. So again, that is zero point 0.8, and then it is 1. And then close end. So now in the setting, by clicking that snap and then major uh, major grid spacing and then steps per major, so it will help you to draw it precisely. Then you can check the dimensions of that and then display dimensions. So general, so here it is 8, then that is 6, that is zero point 0.8, and then this one is 1. So just undo it, and then in the sketching, so that these are the all sketch. So I can go here in the setting again, so turn off the grid, and then in the sketch, so that sketch is being drawn, and here you can see that all the dimensions. So I can just zoom in to check that if all dimensions are appropriate. So 1 centimeter, and then all these are the zero point 0.8, so 6 centimeter, and then the base is 8 centimeter. Okay, so once you have done that one, then you need to extrude that. So now first click on that sketch and then extrude that, and then go to the 3D, and you can see that it is going to extrude that in positive uh, z-axis, and it is its total length is, the length is 6 centimeter. So the length is 6 centimeter. So it is 6. So you can from here reverse its direction to take it to the other way, or you can leave that as normal. And once it's done, then you can generate that, and here you have that sketch. So this is model you have created, okay, and then that is a 3D sketch for that. So this is all about drawing that 3D part. So save that design and then close it. So now you can see there is a tick on geometry. Next step is need to, in the model, need to assign materials. So for that one, double click on model and it will take some time to open. So that is the model, and all the next step, model setup, solution and results. So they will be in this one. So the first step here in the model is need to assign material. So click on the geometry. There is a solid there, and then material assignment here is structural steel. So change it to copper. So now the material is being assigned. But remember that you need to change the units to the standard one, either from there or you can have here change to the standard one. The next step is in the model, construction geometry, and create a path. And for that one, here, home, sorry, in the model, there is a construction geometry and a path, and there is a path here, and it requires that 3 coordinates. So I want to draw it here. So about that one. And for this one, the z-axis is 6 for both one. So I'm going to set those coordinates. So now with the coordinates, so that is the first point right in the center of that base. And that second point is right on the top of that top. So you can see that here. So right in the center. And then here they are right in the center. So that path is being created. Next step is to create mesh with a suitable element size. And for that one, here in the mesh, so element size I am going to use here as 2.2 centimeter. Okay, and then generate. So now the mesh is done and it is quite uniform, as you can see from all sides. So that is quite uniform mesh from all sides. So next step in the setup, need to add boundary condition, steady state thermal, then environment, temperature, and then so scope is geometry, phase, and then the magnitude of that. So for that case, I need to go in the steady state thermal, right click on that, insert temperature, and that's the temperature for the base. That is temperature for the base. So I need to rotate that, and then from here, select that phase, apply, and then the temperature of the base is 80 degrees Celsius. So the temperature of the base is 80 degrees Celsius, and then the other one temperature is 20 for ambient, and 38 is the uh, heat transfer coefficient. So that 80 degrees Celsius temperature is being applied to the base. Next step, need to apply convective boundary condition in the steady state thermal, and then the procedure is the same one. So for that one, here in the environment, click on convection, and then for convection, all the faces need to be selected. So it's very simple, just click the mouse and drag that mouse on all those surfaces. So now that surfaces are being selected, now rotate that, and then again click on the face, and by clicking control button, Then by clicking control button, select all other faces. So now all faces, they are selected other than base. So then apply. So there are 21 faces are selected, and then the film coefficient is the convective heat transfer coefficient, and then 20 is the temperature. So that is being applied to all those surfaces 20 and 30. Next step in the solution, apply to need to required is temperature for whole of that part, and then along that scoping method. So for that one, in the solution, right click, insert thermal temperature, or here you can go in the solution thermal temperature, and this one temperature is required along that path A, and for that scoping method, for that temperature path A, scoping method instead of geometry selection is path, and then need to put path name. So now that is the path name. So two parameters are required. One is the temperature for the whole of the part, and then temperature along the path. So once all that done, then click on solve, and it will take some time to get the results. Next step is results, and need to check the temperature. So for that one, here right click on the temperature, and that is the temperature through temperature distribution through the fin. The base is at 90, and then here in the middle fins there is a uniform distribution of the temperature, and the outer fins is a different one, and then that is the side, and then that is a uniform temperature distribution about that one, and then this one is for the that is for the path, and that is this one is. So one thing is important here, and what is that? That is when you're going to create a path, so you need to set that number of samples, because the total height is 6, and I want 6 centimeter, and I want that temperature distribution about each centimeter. So I'll just put here, like, let's say 9 for each half. Okay, and then I'll solve it again. Now that is the temperature distribution, like at the base is 80, and on the tip of the fin it is 77.31. So that one I can save that. So you can save it somewhere, but for the quick reference, I'm just taking a snapshot of it for reference, and then that is the temperature distribution. So I'll keep that temperature distribution. Now this one is, we are going to use it for reference to perform steady state thermal analysis. So now steady state thermal performed. Now I want to perform that transient thermal, and for that one, 5B now step, need to go to analysis and then get that thermal transient. Okay, so here in the okay, so here home analysis, and now that is transient thermal. So as I'm going to do it, so here in the you will get that B5 as transient thermal. Okay, and then that boundary condition of temperature and convection need to apply in the same way to that transient thermal. So here in the transient thermal need to apply same boundary conditions. So I'm going to apply. So now the temperature and then convection that is being applied. So the next one is in analysis setting, need to set number of steps equal to 120. And here in the analysis setting, the number of steps they are going to 120. So as this solution procedure is going to change, and for transient thermal density and specific heat capacity are also required, so need to change the material here and add those properties. And for that purpose, here in the engineering data, click on engineering data, and now for the copper, need to add other fields. So for that copper, now the physical properties, that density need to be added here, and then specific heat that need to be added to the copper. So the density of the copper is 9000, and then specific heat capacity of the copper is 385. So these properties are added. So need to save it. You save it and then just close it, and then here you can see that only need to update that model. So okay, so this one need to update, so that properties will automatically being updated. Now that setup is updated, so this one need to update as well. So now the setup is being updated, so I need to check that here if the material has been changed. So because you can see that A4 and B4 are the same, and here in the material I can click on the copper, and you can see that the properties like density, thermal conductivity, and specific heat capacity, they are being applied to that one. So now the next step is B6 in the solution need to thermal temperature along that path, and for that one in the solution click on that, insert thermal temperature, or otherwise here thermal temperature, and I am going to rename that as path A, and for that one in the geometry selection need to select that path and then path A for that. Okay, so now that is our solution required. So I'll, and remember that here in the construction geometry, like I have set that 9, so I'll get that because the total height is 6, so I'm going to change it to 11, so that I'll get that two values in each centimeter. Okay, so in the solution, I'm going to apply solve to that. Next step is results, and in results, the temperature. And then I'm going to compare results of steady state analysis with transient heat transfer analysis. So here you have those results, like for transient, that is the temperature distribution. Okay, so that is temperature distribution. So I'll go in the display and I'll set two viewports. Okay, so that is now B transient, and here I am going to put that temperature. So now that is steady state thermal temperature, and that is a transient thermal. So you can see that the maximum and minimum temperatures, so they are almost the same, and here the temperature distribution is exactly the same, and from the side and even from the top view, that are both are same. So that is steady state thermal, and that is a transient thermal. So now temperature along the path in steady state, and that is for, so okay, so that is for steady state temperature distribution, and that is for the transient temperature distribution, and for time 120 seconds, so the solution converge well. And here this is the temperature distribution for, like, the temperature distance, this is the base to the tip, and these are in for each half centimeter. and then these are for steady state thermal. So those values are exactly the same. Okay, so this is comparison of both steady state and transient. And the most important is the time in a transient heat transfer analysis, a transient thermal analysis. So the solution must converge in that time. And as you can see, if I plot the temperature, okay, so like the temperature here, that is the temperature. So that is minimum, maximum, and average versus time. And here you can see for 120 seconds. So it is going to converge well. Okay, so although there is not significant change, like even for there's not much significant change after that, yeah, after 75 seconds. So that is now a comparison of both. So important here is like in analysis setting time that when is going to converge, you need to first, it is recommended, I'm going to recommend that first run steady state thermal to get that what are the results, and then for transient analysis use that time in which the students in which the temperature that converge well, temperature or whatever the parameter, they converge well. So that is end of that steady state and transient heat transfer through rectangular film. So I hope you like this video. Thank you very much for watching. You can leave comments for feedback.